introduce Eric Lyons next. So he's a collaborator from University of Massachusetts Amherst. He's a research fellow and system engineer there in the Department of Electrical and Computer Engineering. So welcome, Eric, and he'll talk about weather feature extraction on the academic cloud for drone route planning. Welcome.
Thanks, Eva. I'm going to actually leave my slides in this mode for now. I've been having technical difficulties when I try to switch to full screen, so sorry about that, but hopefully this will suffice.
Yeah, no problem. We can see them well.
Okay, so, all right, I'm Eric Lyons, as you mentioned, but really this presentation is on behalf of our hosts here, especially George Papadimitriou, who helped quite a bit with this, and also yourself, Eva. And then also on behalf of RENCI, University of North Carolina at Chapel Hill, who also contributed substantially to this. So thank you to them also. Okay, so as Eva mentioned, I think on my slide there, it says that I'm the systems engineer, and this is of the CASA radar network, which is it's a network of 7 operational Doppler radars in the Dallas-Fort Worth region. So what we did is we set up this radar network, and what differentiates it from NEXRAD, which is like the main government radar network that people are generally used to looking at on their TVs. NEXRAD deploys single radars, and they're spaced out quite a bit. They're like maybe 150 to 200 kilometers apart in general. So each single radar operates alone, basically, and it covers a long range. It's very high powered. It can see light precipitation. But because the Earth is curving underneath its long range of view, it actually misses quite a bit of the lower atmosphere once you're at range from the radar. Because as the picture on the left shows, the beam basically travels in a straight line, whereas the Earth's curving, and so the bottom of the beam starts to get quite a bit off the ground. So to try to resolve this problem, we set up this network of short-range, low-powered X-band radars. And one of the key points here is that they operate as a network. So we set up 7 here, so each radar every minute will generate radar data, and this data flows out to our users, which mostly is like emergency management, the weather service. And then there's also users like DFW Airport, local municipal airports, stormwater managers. And so, as I mentioned, these radars, they scan very quickly. And so in order to provide timely information to the stakeholders, there's a lot of analysis, and it occurs not just on a single radar basis, but then often merged together thereafter to produce meteorological products and derivations thereof that are useful and provide information such that our stakeholders can take action. Okay, so one of the chief industries that we're starting to focus on recently, and this is sort of the basis for this talk, is actually looking at providing information for drone guidance. So basically UAM, urban air mobility, as it's called. This is a rapidly developing industry, and they're going to be doing stuff like package delivery. Another early thing that may happen is delivery of like hospital goods, or even organ transplants between hospitals, and also blood, which basically they want to get between hospitals quickly and don't want to have to run into traffic on the way there. So what we want to do is provide weather information to them in a fast way, such that routes can be automated on demand. Another application might be air taxis, where you say we want to get from point A to point B, and these being small aircraft for delivery or air taxis, they're going to be really sensitive to this weather information. So we want to take all this information very quickly and blend it together and provide these products. And all right, another consideration is the weather comes and goes. Quite often it'll be, clear air. There may be some amount of wind above the ground that you have to consider. But thunderstorms, on a given day, there may be there and they may not. And the algorithmic load associated is highly a function of the weather itself, so that if there's thunderstorms around, you actually may need quite a bit more computing than you would if there's nothing going on except for, light winds aloft or something. So the point is that the compute requirements are highly variable depending on what's happening. And so we want to scale our architecture to handle these so that we don't have to dedicate computers all the time that are capable of handling the worst case of the weather, because 90% of the time or even more than that, that's not necessary, and you'd essentially be dedicating these computers when you really don't need them. It would be cost ineffective. So because we want to scale our architecture, though, that has implications on all the processing, and this is one key area that Pegasus is going to help with, because along with the HT Condor integration, it can actually seamlessly distribute these workloads on pools of workers that we can provision on demand. So we use the academic cloud, ExoGENI and Chameleon in particular, to actually acquire resources. And for that, we use the tool called Mobius, which is developed at Renzi, which we can basically, we can instantiate, and we say, okay, we want a certain number of workers and, some node to manage or to run Pegasus and HT Condor. And so Mobius will actually generate a network for us. And then our workflows are set up. I'll talk about the workflows here in a minute. And then Pegasus will distribute the processing accordingly on the network. Okay, so here's an example of some of the workflows that I'm talking about. I'm going to step through this picture here. So at the bottom, this is really like this is sort of the input of this whole workflow. We have 3 different radars. I mean, really, it would be 7. This is like what velocity data would look like coming in from each particular radar. Now, an emergency manager might really have trouble like interpreting what all this stuff means. But really what they want to know is like, do we have high winds over our area of interest and our infrastructure of instance of our infrastructure of that we're interested in. So what we do is we take this single radar data, which again is updating really 3 times a minute, and we feed it into our workflow. The first thing it does is it actually makes pictures. So it generates pictures of this data, like you see here on the bottom. Then we actually pass each of these 7 velocity fields into a function that merges them all together and generates the maximum observed velocity that we see over all points on the map. And then we make a picture of that merged wind field. Then we actually generate contours of the velocity. So for example, severe winds are considered to be 58 miles an hour. So if an emergency manager wants to know where severe winds exist, what we do is after we merge, we have a gridded field of, of our winds, but we actually want to generate a closed polygon contour thereof that describes the area. Now, it may not have to be severe level. It could be, 40 mile an hour winds can cause damage, and there could be multiple contours. So we generate basically a set of closed GeoJSON formatted contours. And the reason that it's helpful for them to be closed is if you see all these little crosses here, these are like hospitals that exist within the Metroplex. And when you have closed objects, you can actually do like inside-outside comparisons. So we iterate through the infrastructure of interest, and we decide whether or not it's within the contour that contains the wind information. So the point is, all this stuff, there's this multi-tiered workflow, and we specify this all into Pegasus, and it can actually go through each of these processes one by one and process them accordingly on the nodes that we have available. Okay, similarly, we do something with hail where each radar provides its base data, and we go through it and we generate a single radar-based hail field, and then we merge them together into a multi-radar-based hail field, and we do the same sort of extraction about where the area of hail is, and then compare it with the area of interest that's on the ground. I'm going to stop my share for just 1 second and share different screen. Okay, this is an example on the website. You see we have this is hail data underneath. This orange contour is the contour of the hail, and this red contour is actually the contour of the wind data, which is not shown. But we can step through as this storm evolves, and you see that this white contour here underneath is the city of Grand Prairie, and this one on top is Dallas-Fort Worth Airport. So as these contours move, we actually compare it with this infrastructure on the ground. And this, again, is happening every minute. And Pegasus is controlling all of these individual workflows and providing this information back. Okay. Let's go back to my slides here. Okay, so all that stuff also becomes a basis for how to steer the aircraft, because those same sort of contour obstacles are what we're going to want to route the aircraft around. Oops. So quickly, when we get our
Oops, Eric, we cannot hear you.
Okay, sorry about that. I'm not sure
There
what
you are.
happened.
Yeah, I'm good.
Okay, so on the left here, we have an architecture here that's deployed on ExoGENI. What we do is actually we set up all of our jobs on containers that exist on this storage node. And we have a submit node, which is where Pegasus is going to exist. And so as the jobs are actually going to be created for this workflow type processing, we're going to actually basically tell the worker nodes here to get a container which exists on the storage node and then execute our job and then pass that information back through our network to our main database that contains all this information that the flights are going to need for routing. So here's an example. So we have a web application where you give a start and stop point. And what you would see is, all right, you want to go from Grand Prairie to Lancaster, or actually vice versa. But in the way, you have these obstacles that the Pegasus workflows have identified. And essentially, you want to route around them. So we assign basically parameters to say, okay, what are the things that the flight wants to avoid? Like, for example, what are the levels of wind that it can't tolerate? And also like the rain rates. And so, so thereafter, you actually have Pegasus extract these thresholds from the data itself. So you actually feed it back to Pegasus and say, from our gridded data that represents the winds and represents the rain rates, generate that GeoJSON contour specifically for this particular threshold level. Okay, so again, just stepping through this, you saw that was our flight generation web app. You generate basically a request. The request goes to a message queue we have, RabbitMQ we use, to say, I want to generate a path and I want to simulate it. And so what you do is your requested path flows to a flight database here. Then Mobius and Pegasus, basically it's reading from the flight database to read out those weather contours shown here at the bottom, these threshold values and the different products. And actually, then it goes ahead and extracts those things with these different workflows here and feeds it into our obstacle database. So at any given time, you could have multiple flights, each with its own contour level that it's interested in. And Pegasus basically takes a superset of all the different contour levels and all the different weather products and generates all these obstacles. And eventually, when the flight routing algorithm happens, it sends a query for, again, based on its JSON descriptor of the weather products that it's interested in. It sends a query for all those products which are now in the database, and all that stuff is returned, and then it's going to generate a path around this stuff. So here's an example. So in this case, these pink lines represent routed paths. And these two different sets represent two different contour levels of, in this case, the same types of products. But in one case, you see that, like this inner contour set, the plane can take a more aggressive route through here. Whereas based on its characteristics, the outer contour set would have to take, this sort of wider route around everything. And again, this is because Pegasus is going through everything and determining, which of these polygon sets are going to be relevant on a per aircraft basis. So basically what happens is we generate this master obstacle set and then we merge it all together. And then we use what's called the A-star algorithm to find the shortest path around this data. And let me just show you an example here. Okay, so what's happening is this whole thing is constantly iterating. The weather is changing rapidly, and our prediction of where the data is also changing. So one thing I think that makes our project a little bit different here is that there's a very strict time requirement. All this stuff has to happen quickly, really like on a 1-minute basis here. You see that this movie is updating 1 minute at a time constantly with our latest prediction of where the weather is going to be in this case. So Pegasus has to operate rapidly, and that can be a little bit problematic just because the planning process can take a while. Now, granted, when you have nodes, something like Pegasus like when you have scaling worker nodes, it may be very necessary to use Pegasus to orchestrate amongst all this stuff. Otherwise, it would get very complex in terms of handling scalability. But I want to show you something here. So this is like for a single job using Pegasus. This is just one single, very simple, fast running job. It took in this particular case like about 1 minute and 14 seconds. Okay. To do that same job from a worker node with the same container, it took only about 1/4 of a second. So there's this kind of penalty for planning. And I think what the implications is that the penalty doesn't scale. In other words, if I process one job or if I process 50 or 100 of these similar workflows, then actually the penalty is almost static and the Pegasus rapidly becomes, just as good or better as the single case. But what it does imply is that you have to be careful about what you're actually going to call Pegasus to work on, because if it's a very simple, rapidly updating job, Pegasus can be overkill and you can start exceeding your timeliness requirements. And so what I've been doing is when I actually generate this stuff, I've been generating stuff at scale. And this is where Pegasus shines, because now you can calculate, like I don't calculate one single threshold level for one flight. I calculate all the threshold levels for all the products for all the flights with Pegasus. And then again, that penalty becomes, sort of irrelevant relative to the amount of processing it's doing. Because again, the planning delay is no longer significant compared to all of the extractions that are occurring. But it is a little bit of a balance you have to consider in terms of what to send to Pegasus, and if it's worth, like in some cases, the checkpointing and various things that Pegasus does, if it's worth using it, using that for simple jobs. So just the last few things very quickly. One thing I would propose is, a REST API for remote job submission. When you have these, things that could be happening all over the place in terms of, and also like on the web, it's nice to be able to make Pegasus requests from various places, and a REST API would be helpful for that. We could consider maybe some sort of lightweight flag you could give Pegasus that might have it skip some of the things that it normally does, checkpointing, maybe some lighter weight metrics, some sort of faster planning. It's not totally clear to me if the planning could be sped up, but maybe for certain jobs, we could, do less rounds of negotiation or whatever it may be. Have some sort of contingency job in planning workflows where you say, okay, if this should be the case, then you continue adding to the workflow. That may even already exist. I'm not really sure. And then one last thing is sort of deeper integration with Mobius so that Pegasus can actually help control the number of nodes that you have available to process on. And in the interest of time, I'll stop here.